right answer. Okay, make sure you chimed in. Yes. These are just if you finish the iClicker quiz. These are just ones for you to start working. Oh, you're seeing if they can converge or diverge. Sorry. That's what we're going to be. That's what we've been doing for a couple sections, and we're going to be doing those for a few more sections. So, sorry, I should have been more clear. Okay. Make sure you're chimed in. 5, 4, 3, 2, 1. Okay. All right, so let's talk about this iClicker problem. What was the first rule of thumb? I think we talked about this. What was the first rule of thumb that I gave you guys when you're thinking about how do you construct another series to do the comparison?
First, if you're setting convergence, you need a function that's greater than it, and then it's divergence.
Okay, so if you're going to do the comparison, if you think it converges, you need something that's larger. If it diverges, you need something that's smaller. But how do you find that function you're going to compare to?
Usually, you find the dominant term.
Okay, so the first rule of thumb is to look at the dominant term in the numerator and the denominator, if there is a numerator and the denominator. So in this case, what are the dominant terms? Well, there's only one in the numerator. What about in the denominator? So the dominant term is the one that's growing the fastest. So 3 to the n. So you would expect that series should be close to this one. It should be close to e to the n over 3 to the n. Okay? So that would be the first one I would try and see if it works. Okay? Let's test it out, shall we? So some of these let's try this. So can we do a strict comparison? Which is larger, e to the n over 3 to the n minus 2 to the n, or e to the n over 3 to the n? Which is larger? This negative 2 to the n makes the denominator smaller, so the whole thing's going to be bigger. If you can't remember, then you just have to think of 1/2 and 1/3. Then 2 is smaller than 3, but 1/2 is larger than 1/3. So you have a hard time remembering that. The denominator is smaller, so the whole thing's going to be larger. So can we do a comparison here? No, because that is larger. It's on the wrong side. Well, first, does this series converge or diverge? How do we know this converges? It's not just because the denominator is larger than the numerator. So the terms here go to 0, right? The terms here go to 0. So what do we know? Nothing. Just because the terms go to 0 isn't enough to know whether it converges or diverges. Yes, that's the key. Nice job. So we can think about that. Think about e to the n over 3 to the n as e over 3 to the n, and e over 3 is less than 1. So this is a geometric series. The ratio is less than 1, because e is about 2.7. So e over 3 is less than 1. So this series converges by the geometric series test. Okay? So we have this convergent series, and it is smaller than this series. And so what can we conclude? Nothing. The series we care about is larger than a convergent series. So what? Okay? It's not enough to say whether it converges or diverges. If it's smaller than a convergent series, we're good. If it's larger than a divergent series, we're good. So what do we need to do? Do the limit comparison test. So let's set up a limit. Okay, my e to the n's cancel out, so that's nice. But I end up with trying to find the limit as n goes to infinity of 3 to the n over 3 to the n minus 2 to the n. And what can I do here? What was that? So yeah, it does go to infinity over infinity. We could try L'Hopital's rule. What's the derivative of an exponential function? It is the exponential function times the natural log of the base. So in each of those cases, we get... And how does that help us? It doesn't. And if we keep doing it, you're just going to keep those core exponential functions there every time. So L'Hopital's doesn't help us here. So what else could we try? Okay, that's a great strategy. Okay, so you recognized we have this 3n over 3n minus 2 to the n, and this, if it had been inverted, would be 3n minus 2n over 3n, and that's nice, right? Because then you could just rewrite it as 3n over 3n minus 2n over 3n, and this one goes to 0. I'm sorry, that one goes to 1. As then goes to infinity. And this one goes to 0 because it's a geometric sequence, and 2/3 is less than... Do I have more room over there? 2/3 is less than 1, so it goes to 0. And so you could go back to the beginning where you set up this ratio in the limit comparison test. Just change which one was in the numerator, which one is in the denominator, and then you would end up with an easier case. And you'd see that the limit goes to 1. So, okay, but what if you didn't want to do that? There's another strategy. Has to do with dominant terms again. So you can just divide by the dominant term in the in the expression. So 3 to the n is the dominant term, so you can divide by 3 to the n in the numerator and the denominator. And then you get 3 to the n over 3 to the n over 3 to the n over 3 to the n minus 2 to the n over 3 to the n. And this one goes to 1. That one is 1. And what happens to this term? It goes to 0 because 2/3 is less than 1. So it's a geometric sequence. So then again, the limit is 1. So the limit is 1. Okay, so what does that tell us? We did that work. What does that tell us? They have the same behavior. The series that we used to compare it to, and this one that we cared about, by the limit comparison test, they either have to both converge or both diverge, and we know that the one we compared it to converges by the geometric series test. So this one has to converge. Right. Yeah, that's the power of the limit comparison test. His question was like, can you still use the limit comparison even if it is smaller, or even if it's larger? Yes. You're saying like this one is smaller than this one. It converges, right? So we can't do the comparison. But the limit comparison test, if they're close enough, and we get that value in that, when we set up the limit with the ratios of those, and if it goes to somewhere between 0 and 1, 0 and infinity, can't be 0, can't be infinity, then we know that they are close enough that they will either both converge or both diverge. So that's the power of the limit comparison test, because you get things that are just on the wrong side, but that shouldn't impact it too much, right? If you have a 1 over n and a 1 over n plus 1, you'd think that plus 1 right there shouldn't Subtracted enough to make it converge. So, and it doesn't in the limit comparison test. Great. Other questions or comments?
So, how is it possible to decide which is the numerator versus the denominator?
Let me make sure I understand your question. So when we set this up in the limit comparison test, I just picked one to be the numerator and one to be the denominator. And your question is like, why can you just choose?
Right.
Yeah. So if this limit came out to be, our limit came out to be 1, right? So if you end up switching those, it'll still end up being 1, right? So the conclusion will be the same. But what if you had another one that you set up where the limit of a sub n, and b sub n went to 2? Well, what would happen if you wrote it as b sub n over a sub n? It would just go to 1/2. And so as long as we only care if it goes to some finite number that isn't 0. It just has to be between 0 and infinity. So in one of these cases, you get a number larger than 1. In the other case, you get a number smaller than 1. It doesn't matter. They still are that ratio becomes a constant, or the limit of those ratios is a constant. It's close enough that they either have to convert or have to divert. It doesn't matter what that constant is.
So when we were signing on the test, you asked us to show this work, and we do either way.
Yep. Yep. You can do either way. Doesn't matter. That's right. So in one case, but in their first case, it went to infinity. But infinity is inconclusive with this test. So you either get infinity or you get 0, and then you can't conclude anything either way with the limit comparison test. So you have to choose. Yeah, you have to choose something better. So great. Thanks for bringing that up. His question was, what if you get a 1 plus 0 one way and a 1 plus infinity the other way? You shouldn't. So, because otherwise you got a 1 and then you got an infinity, and so something went wrong with those limits. So, okay. All right. Let's take these. Here, actually, let's. How do I copy on here? There you go. Does Control V work on this? It does. Great. Okay. So I'm going to rewrite. I'm going to put 2 more problems down here. So go ahead, take time to work on these. These are the ones that we worked on last time, but I know not everyone got to. So I'm going to put a couple more problems down. That's so let me take a second and explain 4 for the students that get that far. So imagine you have infinitely many dominoes, and you're going to start making a stack on the edge of a table, and you want to have your top ones pushed out further than the lower ones, and you're trying to get this edge out as far as you can from the table without them falling over. The question is, how far can you get that stack to reach over the table? Okay. So just to make the setup easier, let's just call the place where this first domino is 0. That front edge is 0. If we don't want them to fall, we have to think about the center of gravity, but they're only rectangles, so we can think about that easily. So I can put the second one. I can put the second one right here, right, where this edge is matched up with the center of gravity of the top one. Can I put the next one right here? No, because these will now, those first 2 will fall. So where could I put that next one? Well, the center of gravity of this one is there. The center of gravity of this one is there. The center of gravity of these 2, it's symmetric, so it's got to be right in the middle here. So I could put that third one right there. So this length is half of a domino. This length is a quarter of a domino, because it's going to be half of a half. Now the question is, where can you put that next one here? And then the next one. How far back can I put those? So that's that problem. Okay. So. Okay. If you're stuck on that first one, that sine of 1 over n, I know I hit it very quick at the end. We'll hit that again. If you're stuck on that one, just move the other. Okay. All right. Let's talk about the first one first. So sine of 1 over n. So I rushed through this last time, so I'll try not to rush this time. So we're taking the sine of something that's getting close to 0. So our strategy is like, what is this close to? Is there another function that's close to the sine of something as it gets close to 0? And so if you look here around 0, oops, I don't have my markers. So if you look here, if we zoom in, what does that start to look like around 0? Yeah, starts to look like a line, right? And which line? Just y equals x. So, and if you put y equals x on there, you can see that, hey, around 0, it is really close. So, and you can, if you start plugging in values that are close, like here, I actually plugged in sine of 0.05. You get really close to 0.05. Like the sine of something around 0 is basically that something. So now you guys will understand this better in a few weeks. Unfortunately, this whole chapter is backwards, but I say that a lot, right? You'll understand this better in a few weeks. But the author of the book was expecting you to pick this up. This is one of the homework. This is an unassigned homework problem from previous calculus classes when you knew something about the sine of x over x, the limit as x goes to 0. So here, what's that limit? It's 1. And that means that sine of x and x, those functions, are basically the same thing when you are around 0. So here, that's the thinking that you need to do. It's like, oh, sine of 1 over n. Oh, as n goes to infinity, I'm going to get something of a sine that's around 0. Hey, I know that that's close to just whatever I'm taking the sine from. So we're going to use 1 over n as a comparison. Okay. I didn't assign this as a homework problem because it's one of the harder ones. So that's why I let you work on it in class so we can talk about it. All right, so how do we actually do that? So sine of 1 over n over 1 over n, limit as n goes to infinity. And how do we do this limit? Yeah, the way it is right now, sine of something that's close to 0 is 0. 1 over something that goes to infinity is 0. So I have it in the form of 0 over 0. So I can do L'Hopital's rule. So L'Hopital's rule, I get the limit as n goes to infinity. Derivative of sine, cosine, derivative of 1 over n. I'm lazy, I'm just going to write it as 1 over the derivative of 1 over n. And in the denominator, it's the derivative of 1 over n. But this isn't bad, because I don't have to take those limits, those derivatives, they'll just divide out with whatever they are. So I end up with cosine of 1 over n. And as n goes to infinity, what does that equal? It's cosine of 0, which is 1. So that means these both converge or diverge, but 1 over n diverges by the p-test. So sine of 1 over n diverges by what test? Limit comparison test. Okay. Guess I don't have to abbreviate test with test there. Okay. Questions on that? Okay. All right. Let's do the next one. Yeah. Okay, that question was, what's the p-test? So the p-test, oops. If you have a series of 1 over n to the p, where p is a constant, then the series converges if p is greater than 1. So, does that help? And it diverges if p is less than or equal to 1. Okay. So, p-test might give you some intuition about this problem. So, if you look at this, this is almost like the p-test. I have 1 over n to the something, and this something is, and that's always greater than 1. So, what should we conclude? Yeah, if you do, you're wrong. So, you can't do this by the p-test. It's not of the form of the p-test. The p-test only says something if p is a constant. So, so this is like borderline right here. You're like, it seems like it should converge because it seems like it's barely larger than the denominator is barely larger than 1 over n. So maybe it should break over that. But any other series, you give me like 1 over n point 0.00000, however many zeros you want to give. Well, you can't say that this series is larger than this series, because eventually that n's going to be smaller than that. You're going to end up with an exponent that's smaller than that, and so you're not sure if it behaves the same way. So what can we do? Let's do a comparison or a limit comparison test. But what are we going to compare it to? 1 over n, because this piece right here, it goes to 0, so you might think maybe 1 over n might be close enough. So let's try that. Oops. Limit as n goes to infinity, 1 over 1 plus, let me do 1 over n, over 1 over n to the 1 plus 1 over n. You can do it either way. This works out just a little bit nicer. So simplify. So we get n to the 1 plus 1 over n, and that's the same as, I can think about that numerator as n times 1 over n. Okay? Right? This is like n to the 1. That is n to the 1. So n to the 1 times n to the 1 over n, that's the same as this. So that makes this nice, because then these divide out, and I have the limit as n goes to infinity of n to 1 over n. Yes? Yeah. So the question is there some max of a difference you can have with the functions, with the limit comparison test, so that it doesn't work? And the answer is yes. If the limit goes to 0, if it's big enough difference, the limit will go to 0, or the limit will go to infinity. And then you know if they're not close enough. Yeah. So, good question. Okay. All right, what's the limit of n to the 1 over n? You can also think about that as the nth root of n. So, what does that equal? Yeah, it is, you get the infinity to the 0. It's that form. Does everything of this form, go to the same thing? Nope, it's inconclusive. There are some forms that always go to the same thing. Like, if you have 1 over infinity, that's always going to go to 0. Doesn't matter what it is. Okay? But this is an inconclusive, so it's indeterminate. So we use our natural log trick here. We're going to rewrite this as e to the natural log. Well, let's pull the limit out. And then we can use our natural log rules, and moving the limit inside using limit rules. So 1 over n natural log of n. And here, let's rewrite that. E, the limit as n goes to infinity of the natural log of n over n. So here, as n goes to infinity, I end up with an infinity over infinity. So let's do L'Hopital's rule. So L'Hopital's gets us e to the limit as n goes to infinity of 1 over n over 1. That's nice, because that is just e to the 0, which is 1. Okay, so that means that this limit that we set up way back here, that this one, it equals 1. So that means that these series either both converge or diverge, and we know that 1 over n diverges by the p-test, so this series diverges by the limit comparison test. Okay. So here, your intuition using the p-test leads you astray, so you've got to be careful. So, yep. Oh, you bet. Make it down there. Yeah. Oops. Okay. All right. So, what was that last problem? This one. I guess this isn't the last problem. We're not going to get to our domino problem today. We haven't had time to do a lot of the fun application problems. There's one coming up in lab later this week. So, all right. Snap if you had time to work on this problem. Just a few. Take 1 minute to think about this problem before you do it as a class. All right. So, what's the most dominant term in this expression, in this entire expression? This thing. That's going to go to infinity. Here we've got a constant. Here we've got something. This numerator is bounded by 1. Okay? So we're going to use that. So the worst case scenario, with series, you want to think worst case scenario. And the worst case is you're adding up things that are bigger. Right? We're adding up infinitely many things, and if we want to do comparisons, you can think about, well, the worst case, at least if you think it converges, is to make it as big as possible. And so the largest you can make sine of n is make it 1 the entire time. So which is larger? Which is larger, this or this? The one on the left or the one on the right? The right. The numerator is always larger over here, so that means that the inequality goes this way. Larger than or equal to. And, oh, why did I do 1 right there? There. Okay. It's a really large 1. So 1 equals 5. Okay. And then what about this series compared to this series? Larger or smaller? It's also larger because the denominator here, the denominator there is larger, so the entire expression has to be smaller. And what do we know about this one? Yeah, that's 1 over n to the 3 halves. So this problem is actually one from a previous final exam. So this converges by the p-test. So what can we conclude about this series? Yeah, so this series converges by the p-test. I'm sorry, by the comparison test. Now, this is one example. I think I said previously you can always use a limit comparison test if you're not sure about which side it's on. This is an example where the limit comparison test doesn't help. It's inconclusive because you end up with a limit of just the sign as n goes to infinity, and that doesn't converge. So you have to use the comparison test here. All right, have a great day.